Sorry for this technical inconvenience.
It's good.
I will be speaking, so you can hear me. I will be speaking about pneumatic superconducting state in iron this near optimal whole topic. So these are different pneumatic state that what we observe usually in the bulk superconductors. Here we investigate thin fields of 0.5, 0.5, 1 to 2 compounds, and the difference is that we don't observe the pneumatic state in the normal phase, but we observe it appearing immediately when we cross the normal superconducting phase boundary. To prove this, there were many experiments done, and these are people who made experimental work. The most experiments have been done in the group of Professor Mishalkov from KU Leuven, but also some other groups have been involved. I will be speaking only about the theoretical interpretation of this data, which have been done in our group. Let me shortly remind about the diagram for 1 to 2 superconductors. We have a dome, the stripe magnetism, so it expands both in the electronic doped and hole doped domain. If we take the barium compound as reference, so at low temperature, this dome already appear some superconductivity. The dome is surrounded by the domain of spin, pneumatic spin fluctuation, and there is a dark domain, pneumatic spin state. In pneumatic spin state, we have other parameter which corresponds to the breaking of tetragonal symmetry. So what is pneumatic state? Let me remind. Pneumaticity when we break tetragonal symmetry to C2 rotational, two-fold rotational symmetry, but we don't break the time reversal symmetry. So here the domain of pneumatic state is this two-fold symmetry. So we have the breaking of say four-fold symmetry to two-fold symmetry, but we still don't come to the stripe magnetism. So there is no magnetism. And this other parameter can be different. So there are many aspects of tetragonal symmetry breaking. It can be just structural phase transition. It can be orbital disproportionation, population XZ and YZ orbitals. And it can be of pure spin state. It is called spin-induced easy pneumatics. So it corresponds to average magnetization, difference of average magnetization x square and magnetization x and y directions. So which are basically difference in the susceptibility in the XX and YY component. So in this domain, we have broken this symmetry. So this is the other parameter in the case of easy pneumatic spin easy pneumatics. In this domain, the stripe magnetism is 0. If you go higher, we are in the domain of fluctuation, where also this order parameter, pneumatic order parameter is 0, but you have important fluctuations of this pneumatic order parameter. And finally, if it goes down by temperature, we come into a stripe magnetic domain, where also there is orthorhombic in all aspects. So here we have also different from 0 the magnetization. So we are interested in the domain of 0.505. So it's 50% doping. It is close to optimal hole doping, but it is to the left. So in this domain, we don't have any of this symmetry breaking. We don't have orthorhomicity in any aspects. We don't have the even important pneumatic fluctuations. So we have pure tetragonal phase. So in this domain, we measure for this compound the magnetoresistance and the second critical field. So this is the experimental setup. We have samples which are about thickness varying from 1 to 3 nanometers. The diameter of this sample is 80 nanometers. This is Cordino disk setup for the measurement of resistance, from which we extract the resistivity. And we were interested in measuring the resistivity in the transition domain. So this is a transition between say normal and superconducting state. It is not so it is happening in some temperature domain depending on applied field. If field is not applied, it is quite sharp, pointing to an ordered structure. Actually, these are single crystals of iron arsenicum layers. They are single crystals, but we have 50-50 barium and potassium ions, which are also more or less ordered. That is why we are closer to a clean limit. When we apply the magnetic field, this domain starts to increase as usual, and we investigate these resistivity curves at different applied fields and different orientations. So orientation we measure in plane magnetic field is applied at different directions, which are measured with angle theta, which is taken from AB axis, one of these axes. So what we expect in the case of tetragonal symmetry? We expect that this magnetoresistance is having a tetragonal shape. But actually what we observe when we come in the superconducting domain, we observe that magnetoresistance have a pronounced C2 symmetry. So it is has a pronounced pneumatic character. And the increasing temperature coming to the normal phase, this becomes more and more circular, and it's perfectly circular already in the normal domain. So normal resistivity is perfectly circular. So we have no any pneumaticity in the normal state. So these experiments have been, the measurements have been done on the field-cooled regime. So we applied the field in the necessary direction of 150 K, then we lowered the temperature, then we rotate from this position to another direction of field, and again measure the resistivity. So these measurements, it can be some remaining metastability, because in the new position the superconducting state will not relax to its equilibrium. So that is why we repeated the measurements with field-cooled measurements for each direction. So for each direction of applied field, we started to cool from 150 K, and we the results are shown here by open circles, and we see that they basically coincide with the previous measurements, which we didn't do field-cooled in each direction. So we can say that we can rule out the metastability effects. So what we measured, and these are HC2 measurements, we extracted the second critical field from these measurements. So to do so, we redraw the resistivity curves. So we measured initially the resistance as function of temperature for different applied field values and directions. And now for a fixed temperature, we take a cross of these curves, and we obtain the resistivity for a fixed temperature, but as function of field, of applied field. And for different directions and different temperature, we obtain a family of such curves. So here they are shown two such curves, resistance as function of field, resistivity as function of field, and for different directions. And then we extract from these curves the second critical field. So by definition, second critical field is a field when the superconductivity starts to be destroyed. So it is somewhere we can say we took as reference 90% of this resistance. So we draw a horizontal line, we find the point where this field corresponds the field at which start to destroy superconductivity for a given temperature. Then for another direction, we take the same. We find a different field. It's like here, shown by blue. And doing this for several different directions of field for a given temperature, we obtain such a curve which shows the second critical field as function of direction of applied field in the plane, and we see that it has a pronounced C2 feature. So in the case of tetragonal symmetry, we should have had maximum oscillation of the period of 90 degrees, but here we have 180 degrees oscillation. So this is a feature of pneumatic feature, and we want to emphasize that this only we observe for layers, for thin samples, not for bulk superconductors, where it's a perfect tetragonal symmetry. So we want to emphasize that this phenomenology falls out of some standard paradigm, how it is explained, the pneumatic superconducting state. Usually, if you do this in this Blanda, we have to introduce the order parameter, pneumatic order parameter, which has C2 symmetry, rotational symmetry. And to have a term in the Ginzburg-Mendel function, we have to multiply by a combination of order parameters, which also have C2 symmetry. Each symmetry in tetragonal reference, this is S or dx squared minus y squared, it has fourfold rotational symmetry. So to obtain twofold rotation, we have to take combination of them. So we have to add such a term. It has C2 rotational symmetry. And coupled with phi, it gives an invariant in tetragonal reference symmetry. So if we analyze now the Ginzburg-Mendel this approach, and we have two possibilities to obtain pneumatic superconducting state. Either phi is initially already of lower symmetry in the electronic in normal phase, so phi is different from zero. This is the case of electronic pneumatics. And when we come to superconductivity, we have nucleation of superconductivity. This term can admix to the dominant superconducting component also some subdominant one, and together they define the pneumatic superconducting state, the combination. But this is not the case because we have phi equals 0 in the normal phase. Another possibility is that again, due to this term, in the moment of nucleation of superconductivity, this term will give rise to some delta B if delta S is dominant, and some phi. They will nucleate also. But if we analyze this possibility that phi is only nucleated in superconducting phase due to this term, then how to find its equilibrium value? We have in Ginzburg-Mendel also term phi squared, 1/2 phi squared, yeah? When we minimize with respect to phi, we obtain the phi equilibrium is just this product of this other parameter. If you substitute that in the Ginzburg-Mendel function, we obtain terms of 4th power delta S delta B. The moment of nucleation, these terms don't play a role. So all symmetry lowering of this type will not show up in the high, the second critical field, which in this way will always show only tetragonal symmetry. So this standard scenario cannot explain the phenomenology which we observe. So if we summarize, so we have very weak anisotropy or no anisotropy in the normal state. I mean anisotropy with respect to C4 symmetry. But the pneumatic state strongly manifests in the transition from normal to superconducting state. Because of this, we can suppose that the pneumaticity in superconducting state is something intrinsic to this superconducting state, so we call it pneumatic superconducting state. Well, this is, we show again how it will change the phases. In the case of usual pneumatic state, we come from fluctuation, pneumatic state, antichromatic phase that exists, and then anisotropic C2 superconducting state. In our present case, we have completely different behavior. We have normal tetragonal phase, maybe with very small anisotropy, which is even not observed in its measurements. And then we immediately, after crossing normal phase boundary, we have a strong C2 character of superconducting state. To describe this, we use linearized Eilenberger equation, because we are going to describe the nucleation of superconductivity to derive the second critical field. For this, it is sufficient to use linearized Eilenberger equation. These are these two equations. I will not enter in details. So the only thing we have to say that the input to solve this equation is the pairing potential, is a Fermi surface, and the Fermi velocity. And then we do the solution of this. We can do by iteration till fourth power of this product of Fermi velocity and generalized momentum by generalized momentum. This is the derivative of the coordinates, position of pair, minus E over C A. A is a vector potential corresponding to applied magnetic field without renormalization, because in the moment of nucleation, the field which is within the sample coincides with applied field. It's a homogeneous field, though the problem is relatively simple. You don't have to recalculate the field profile everywhere. Okay, to do these calculations, we need to know electronic structure. The electronic structure for 1 to 2 is known, so we took the parameterization type binding, which is have been extracted from LDA calculations of this optimally doped compound. In the rigid band approximation, we recalculated the Fermi surfaces. I obtained something like this. So then we need, from this we have the Fermi surface, Fermi velocity, and the third ingredient is for this Eilenberger equations is the pairing potential, which also in principle can be calculated, extracted from some first principle calculations. But in our case, we have a more modest goal, and we want to only simulate this pairing potential. So we want to represent it. We know that in principle this is it is an Hermitian matrix with respect to Kf and Kf prime indices, and it can be diagonalized. That means it can be brought to the form which we have product of some functions phi I of K with some eigenvalue Gi. Or this is equivalent to solve this kind of eigenvalue equation. So we can extract phi I and Ji in this case. So they are orthogonal in this way. So actually, this Gi multiplied by total density of states on all Fermi surfaces, all pockets, it is defining the pairing strength, conventional pairing strength. So actually, we need not all the components, but we take only some components for this phi I. We take only the components which we know that they are important for our superconductors. So 1 to 2 compounds, it is known that in the limit of doping of strong hole doping, extreme hole doping, we have D wave superconductivity, and for weak hole doping, we have S wave superconductivity. So we are somewhere here, and this is the region we expect that these two superconducting states will cross. The free energies will be close to each other. So, and at this closeness quasi-degeneracy, this is a key point of the explanation of the observed pneumatic superconducting state. So, in terms of irreducible representation of tetragonal group, so the one of the dominant components is either S or D, depending how close you are to one limit or another. They should be included because they are close. And then to explain the symmetry breaking which can appear, we have to admit some other superconducting state, which is should be of X, Y, or G symmetry, it should have be of B to G symmetry, because the product of this is B to G. And no, not product of this. This is of different symmetry. So this is exactly what will give you. This is actually the minimal model which he used to describe the superconductivities of GI. These are coupling strengths for the two close states, and G12 is a mixing of these states. So this will describe the mixing. This function phi, they are in principle they are known. I will not describe this. This is a simulation of HC2. If you take only two states, for instance S and D, mixed by dxy, for instance, you obtain this blue curve, which is have maximum minimum of 135 degrees exactly. But in experiment is closer somewhere to 120. So in this case we have to mix some other state, the third state, dxy. So from these curves we can see that actually the phenomenology is explained by mixing three states, one dominant and two subdominant superconducting states. And then there are many scenarios. The best is this, that S is dominant and another two are subdominant. So if this is correct, we have also made measurements for plus minus say 0.5% of doping. So in all these regions we obtain this phenomenology. We obtain the pneumatic superconducting states. Then we simulated the magnetic resistance with the Anderson-Kim model or some variation Kim model. So the only input is sufficient to describe this. This is a simulated magnetic resistance. This is simulated magnetic resistance. We see indeed that we can simulate the slopes, C2 lobes, and their dependence on the temperature. This is simulated quite well. So probably the model is correct. So there are some, what is the support? The support for this model is, first of all, the two of critical temperature for two of them should be close. We will have this. The evidence is, there is some Raman, some old results, probably there also, which show that the subdominant component is quite strong strength has compared to dominant component. There were some simulation theoretical showing that variant parameters we can make close the two superconducting states. The final strong evidence is from our earlier work measuring the dependent current in these compounds, and it shows some kick. When we simulated this volatile, we obtained that the simulations show that the two critical temperatures corresponding to the two mixing, even if they are not mixed here, they are close. The relative temperature is about 0.9, which is in line with our simulation. We also obtain this. Okay, then I'm finishing here. So saying that it was observed the pneumatic superconducting state in compounds, 1 to 2 compounds, thin fields of 1 to 2, close to optimal phase, optimal doping. And this is an intrinsic property because the form of this magnetic resistance, it was obtained for different samples, different thickness. The general form is the same. So it is only due to the mixing of some states, which is intrinsic property of this superconductor. That is why we call it pneumatic superconducting state. Okay, I finished here. I thank you for your attention.
Thank you.